Welcome to Unit 8, Lines and Planes, Lesson 6, Intersection of Planes. Um, we're going to split this lesson into two. We're going to start with two planes, and then we're going to go to three planes. So the first part is, of course, two planes. It says, given two planes in three space, there are three possible ways of intersection. So two planes, again, what I'm going to do is I'm going to give you um, plane 1 and plane 2 defined in scalar form. And of course, we know the normals here of both planes. So what does that mean, Mr. Wells? Well, there are really three cases. Case 1 is this. The planes intersect in a line, and so there must be, if they intersect in a line, an infinite number of solutions. So there we go. Here we can see that the normals are not parallel. That means not scalars of each other, which is really what this is saying. And so if they're not scalars of each other, then they intersect in one line. We'll see an example of that in a few minutes. Next one. The planes are parallel and distinct. The planes do not intersect, so then there is no solution. The planes are parallel. That means that one is scalar of the other. However, the d values, and I don't really agree with this, this should really say d1 is not equal to a d2. So they're not scalars of each other. The constants there in the equations, and that just means that they are distinct, so they are different planes. All right, the third case is where the planes are coincident. They are the same plane, and so here they would be infinite number of solutions. They are really the same plane, and here we can say that the normals are scalar, and same thing with the constants, they are also scalar, so they are not distinct, or what we call coincident, going back to grade 9. All right, so those are the three cases, just like grade 9 math, with lines in 2 space, planes in 3 space, same criteria. However, there's either infinite solutions or no solutions, and you can see case 3, infinite solutions, and case 1, infinite solutions as well, but this brings up the fact that there's actually different types of infinity, because you can see here, this infinity would be much smaller than this infinity here. Now, we're not really going to get into that in high school math. However, it's always an interesting thing to think about, and you might see it in university if you decide to take math far enough. All right, let's go to examples. We're going to do 3 examples, and that will be the lesson. So the first example, describe how the planes intersect and the vector equation lines intersect. So first thing you always want to do is look at the normal. So here I can see normal 1 is equal to 3, 6, 9, and normal 2 from plane 2 is equal to 1, 2, 3. So I can see here that if I multiply normal 2 by 3, I get normal 1. So I know normal 1 is equal to 3 times normal 3. So that means that they are parallel. Now, are they distinct? Good question. So to figure out if they're distinct, I look at the d values. And I look, does d1 equal 3 d2? My apologies here, sorry, that should be n2. 3 d2, so this would be 5 is equal to 3 times 5, and of course, whoops, and of course, this is clearly not the case, so that means, what does that mean? That means that the planes are distinct, and that means that there are no solutions. All right, there's the first one. Let's look at the second one. So again, we'll compare the normal. So here I can see normal 1 is equal to 2, 4, 6, and normal 2 is equal to 3, 6, 9, and I can see here that if I do normal 1 and I multiply normal 2 by 2 over 3, that they are scalars of each other. So that means that they are parallel. All right, let's check out if they are distinct. So again, what I want to do is I want to look at the d values here, and I want to see that does d1 equal 2/3 d2. Well, let's check that out. So 6 is equal to 2 over 3 times 9. And here that means 6 is equal to 6, which is definitely true. That means that the planes are coincident. One plane is actually the other plane, and that means that there are infinite solutions. All right, last case, here we go. If I look at the planes here, I can see, oops, n1 is equal to 2, -1, 1, and n2 is equal to 1, 1, 1. Clearly, n1 is not equal to some sort of scalar times n2. Oops. That means, therefore, not parallel, which means they intersect in a line. All right, well, how do we solve this, Mr. Wills? Well, we are going to do a little stacking and attacking, which is a fancy term for elimination. So what I'm going to do is I'm going to take my two equations, 2x minus y plus z equals 1. I just brought the constant over. Same thing here. X plus y plus z equals 6. And I'm going to eliminate one of the variables. I choose which one I want to eliminate. It doesn't matter. So I'm going to eliminate the y as y because they are the same coefficient but opposite signs. That means I can easily add here. So I'm going to add. So I'm going to get 3x plus 2z equals 7. Now what do I do here, Mr. Wills? Well, I'm going to randomly assign one of the variables t. What do you mean by that? Well, I'm just going to say either x or y is t. So here I'm going to say let x equal t. Well, how does it help me? And that's really important here. So I'm just going to make sure I highlight that so I remember. So x is equal to t. So what do I do here? Well, I'm going to replace my x with t. So I have 3t plus 2z is equal to 7. Well, I'm going to now isolate for z. So I have 2z is equal to 7 minus 3t. Divide every term by 2. And so I get z is equal to 7 over 2 minus 3 over 2t. And there's my second one. And what I'm doing here is I'm forming a parametric equation of a line. So I've got x and I've got z. So what do I want now? Well, I want y, of course. So what am I going to do? I'm going to choose one of my planes, and I'm going to substitute this into one of my planes. I'm going to substitute this into plane 2, y plane 2, Mr. Wills, because it's really nice, x plus y plus z minus 6 equals 0. So I'm going to substitute in plane 2. So I'm going to have this, x. Instead of writing x, I'm going to write t. So I'm going to have t plus, I don't have a y, so it's just y, plus, now I've got a z, so my z is going to be 7 over 2 minus 3 over 2t, and then I got here minus 6 equals 0. And hopefully you can guess what I'm going to do here. I'm going to isolate for my y. So here we go, isolate for y. If I just add some like terms here, I've got y. Now t minus 3 over 2t is minus 1/2 t. So I've taken care of my t's. And then I've got a 7 over 2, which is really 3.5 minus 6. So I make this 12 over 2, so I really have here a minus 5 over 2 is equal to 0. And so my y is actually equal to 1/2. Whoops, let me redo that, sorry. Y is equal to 5 over 2, I'm going to do the constant first, plus 1/2 t. And so there is my third one. And I've actually just created a parametric form of a line. And so what's my final equation? Well, my final equation is the line of intersection will be, therefore, line of intersection is, here we go, x, y, z is equal to, look at the constants of the x. So there's no constant of the x here, so it's going to be 0. The constant of the y is 5 over 2. And the constant of the z is 7 over 2. Plus t, and now I just take all the scalars of t. So I look at my x, the scalar of, or sorry, the coefficient of the t is 1, so I have 1 here. The coefficient of the y is 1/2 here, and the coefficient of the t here is -3 over 2. And there we go, there are the three situations. Of intersection of two planes, and that's where the lesson will end, and I'll pick it up with three planes.